What if the greatest discoveries in science are the questions we still can't answer? From the nature of time itself to the mystery of human consciousness, there are limits where even modern science quietly pauses. Tonight, we're exploring those edges, not with speculation, but with calm, documented curiosity. Welcome to Relaxing Facts Studio, where complex ideas are explained clearly, thoughtfully, and without hype. In this documentary-style journey, you'll discover why some mysteries remain unsolved, what they reveal about the universe, and how uncertainty itself drives human progress. Settle in, slow your thoughts, and let curiosity lead the way. Science is often seen as a machine for producing answers, but its real power lies in knowing where answers end. Every scientific discovery begins with a question, and the scientific method is designed to test ideas against reality through observation, measurement, and repeatable evidence. Yet this method has a natural boundary. It can only study what can be observed, measured, or indirectly inferred. When questions move beyond testable evidence, science does not fail, it simply pauses. This leads to an important distinction. Some questions are unanswered, meaning science expects progress as tools and data improve. Others may be unanswerable, not because they lack importance, but because they fall outside what experiments can test. Questions about why the laws of physics exist or whether reality has a purpose may never fit inside a laboratory framework. Recognizing this boundary protects science from speculation while keeping it intellectually honest. Uncertainty, often misunderstood as weakness, is actually one of science's greatest strengths. Admitting what is not yet known prevents false certainty and opens space for discovery. Many breakthroughs from gravity to quantum mechanics emerged because scientists openly confronted gaps in understanding rather than hiding them. Equally important are the assumptions and models science relies on. Models simplify reality so it can be studied, but simplification always leaves something out. When a model works, it explains part of nature, not all of it. When it fails, that failure becomes valuable data, pointing toward deeper truths. Unanswered questions are not signs of limitation alone, they are engines of progress. They remind us that knowledge grows not from certainty, but from curiosity, guided by discipline. Imagine reaching the edge of everything we can observe and realizing the biggest questions begin before that point. One of the deepest mysteries in science is what, if anything, existed before the universe began. Current cosmology can describe how the universe expanded from an extremely hot, dense state. But when we ask what came before that moment, our equations fall silent. Time itself may have started there, making the idea of before difficult to define. Equally puzzling is why the universe follows the specific laws it does. The constants that govern gravity, electromagnetism, and nuclear forces appear finely set. If even one were slightly different, stars might never form, chemistry could fail, and complex structures, including life, might be impossible. Science can measure these values with precision, but it cannot yet explain why they have the values they do. On the largest scales, the universe reveals another mystery: vast cosmic filaments forming a web-like structure that connects galaxies across unimaginable distances. While gravity helps explain how matter clumps together, the exact patterns and uniformity of this structure are still being studied. Simulations come close, but they don't capture every detail we observe. Perhaps most striking is how the universe appears balanced for complexity. It is not chaotic enough to collapse instantly, nor simple enough to remain empty. This delicate balance allows matter to organize into stars, planets, and eventually observers capable of asking these questions. These mysteries do not signal failure, they mark the frontier where observation ends, theory stretches, and curiosity keeps science moving forward. Most of the universe is invisible, and its hidden components may be the key to understanding everything we see. Observations of galaxies and galaxy clusters reveal a puzzling truth. The matter we can detect, the stars, planets, and gas, makes up only a small fraction of the total mass. The rest, something we call dark matter, exerts gravity but does not emit, absorb, or reflect light. Its presence is inferred from the way galaxies rotate and how clusters bend light through gravitational lensing, yet no telescope can capture it directly. Dark matter behaves unlike ordinary matter. It doesn't clump into stars or planets, and it barely interacts with itself or the visible universe, making it ghost-like in every sense. Its mysterious nature challenges scientists to rethink fundamental assumptions about particles and forces. Competing theories, from exotic particles to modifications of gravity, are being tested, but none have provided a definitive answer. Even more mysterious is dark energy, an invisible force driving the accelerating expansion of the universe. Unlike matter, dark energy seems to push space itself apart. Observations of distant supernovae and the cosmic microwave background show that this expansion is speeding up, a phenomenon completely unexplained by conventional physics. Its influence dominates the universe's future, shaping its ultimate fate. Current instruments are unable to detect dark matter or dark energy directly. Particle detectors, telescopes, and space probes can only measure their effects on visible objects. This limitation does not halt discovery, it guides it, forcing scientists to innovate, theorize, and refine experiments. Understanding this missing 95% of the universe could transform our knowledge of physics, cosmology, and the very fabric of reality. Even invisible, these mysteries define the universe itself. Consciousness is still one of the most puzzling frontiers in science, because unlike physical phenomena, it cannot be pinpointed in one location. Brain scans reveal networks of activity spanning multiple regions whenever we are aware, but no single area produces awareness on its own. This distributed pattern suggests that consciousness emerges from complex interactions rather than a single seat of the mind, challenging traditional ideas about cause and effect in the brain. Philosophers call this the hard problem of consciousness, explaining subjective experience, or what it feels like to perceive, think, or feel. While neuroscience can track information processing, firing neurons, and chemical signaling, these mechanisms do not capture the inner quality of experience itself. How does electrochemical activity transform into awareness? This question remains unanswered, and it drives debates in both science and philosophy. Consciousness also fluctuates in ways that are still mysterious. During sleep or under anesthesia, awareness fades, yet some brain activity continues. Dreams, lucid or otherwise, reveal that consciousness can be partially active even when we appear unresponsive. Understanding these transitions could illuminate why consciousness is fragile, how it recovers, and what it truly represents. Measuring consciousness scientifically is another challenge. Metrics like brain complexity, connectivity, and responsiveness provide clues, but they do not fully quantify subjective experience. Researchers are developing innovative methods to correlate neural patterns with awareness, yet no formula can capture what it feels like to be conscious. Consciousness, therefore, is not just a byproduct of the brain, it is a profound mystery. Exploring it reshapes our understanding of identity, perception, and what it truly means to be alive. Each new study uncovers more questions than answers, reminding us that awareness itself may be the universe's most enigmatic phenomenon. Life began in a world that was violent, chaotic, and utterly alien to what we see today. Yet somehow, in this primordial environment, chemistry gave rise to biology. One of the greatest mysteries is how non-living molecules organized into living systems. Amino acids, nucleotides, and simple lipids were present on early Earth, but the process that combined them into self-sustaining, replicating structures remains elusive. Experiments have recreated some building blocks, but bridging the gap from chemistry to the first living cell is still unsolved. Equally puzzling is how quickly life appeared. Fossil evidence suggests life existed on Earth as early as 3.8 billion years ago, not long after the planet stabilized from heavy asteroid bombardment. This rapid emergence raises questions. Was life an inevitable outcome of chemistry under the right conditions? Or did a rare series of events make it possible? The speed with which life began hints that certain chemical pathways may naturally favor complexity, but science cannot yet confirm which mechanisms were involved. At the heart of the mystery lies the first self-replicating molecules. RNA, with its ability to store information and catalyze reactions, is a leading candidate, but exactly how these molecules formed, replicated, and evolved without the machinery of a cell is unknown. Understanding this process is crucial because replication is the defining feature of life. Finally, scientists are still debating whether life's origin was inevitable or accidental. If inevitable, similar planets could host life frequently. If accidental, Earth might be a singular miracle. Each discovery pushes us closer to answers, but the origins of life remain a frontier where chemistry, biology, and cosmic history intersect, inviting us to explore one of the universe's most profound mysteries.
Time flows in one direction. Yet the reason for this relentless forward march remains one of science's deepest mysteries. Entropy, or the gradual increase of disorder, offers part of the explanation, but it does not fully account for why we never experience events in reverse. While equations in physics often work equally well forward or backward, our experience and the universe itself seems to favor a clear temporal arrow, challenging our understanding of cause and effect. Another fundamental question is whether time exists independently of matter. General relativity links time to the fabric of space, stretching and bending around mass and energy. But if the universe were empty, would time still flow? Some theories suggest time may be an emergent property, arising only from interactions between matter and energy, rather than a universal constant. This idea reframes our understanding of existence itself. The limits of physics become even more apparent when relativity and quantum mechanics clash. On cosmic scales, relativity governs stars, galaxies, and the expansion of space. On microscopic scales, quantum mechanics describes particles behaving in ways that defy classical intuition. Reconciling these frameworks into a single theory of everything remains unsolved, and each extreme reveals aspects of reality that challenge the other. At extreme scales, reality behaves differently than expected. Black holes warp space and time to unimaginable degrees, while subatomic particles exist in states of superposition, seemingly everywhere at once. Predictable rules break down, and our classical intuition fails. These anomalies are not just theoretical, they reveal that the universe is stranger than our daily experience suggests. Understanding these limits may one day allow humanity to unify the laws of nature, but for now, time, reality, and the very structure of existence remain profound mysteries.
Across the universe, we observe phenomena that defy easy explanation, challenging scientists and capturing imaginations alike. One of the most puzzling discoveries is fast radio bursts, or FRBs, intense millisecond-long pulses of radio waves originating from distant galaxies. Despite tracking hundreds of these bursts, their precise sources remain unknown. Patterns emerge, yet no single model explains their energy, timing, or repetition, leaving astronomers searching for answers. Closer to Earth, rare atmospheric lights continue to intrigue researchers. Events like sprites, jets, and elves, brief flashes of high-altitude electricity, appear above thunderstorms in patterns that are still not fully understood. These lights reveal interactions between the Earth's atmosphere and the electrical environment of space, yet no single theory captures all their behaviors, making them a frontier of atmospheric physics. On a microscopic level, quantum mechanics presents behaviors that defy common sense. Particles can exist in multiple states simultaneously, entangle across vast distances, or seemingly pop in and out of existence. These behaviors have been repeatedly confirmed, yet their implications for reality and causality remain mysterious. Quantum phenomena challenge assumptions about determinism, locality, and even the nature of observation itself. Even biology presents anomalies that science struggles to explain. Certain species exhibit extraordinary abilities, like magnetoreception in birds, extreme regeneration in starfish, or the sudden appearance of antibiotic resistance in microbes that are documented but not fully understood. These capabilities push researchers to reconsider the limits of evolution, physiology, and environmental adaptation. Collectively, these strange yet documented phenomena remind us that observation often outpaces understanding. Science is constantly expanding, yet the universe and life itself continues to surprise, revealing mysteries that are real, measurable, and waiting to be unraveled. Even with the most advanced instruments, science encounters boundaries that technology alone cannot cross. Measuring the universe at cosmic and quantum scales pushes devices to their limits. Telescopes can observe galaxies billions of light-years away, yet subtle phenomena like dark matter remain invisible, detectable only through indirect effects. At the quantum level, particles exist in fleeting states that challenge even the fastest detectors, making direct observation nearly impossible. These limits are not due to lack of effort. They reflect fundamental constraints of scale, energy, and resolution. Simulations, no matter how powerful, also face intrinsic limits. They can model galaxies, climate, or molecular interactions, but a computer cannot replicate every detail of a dynamic, interconnected system. Simulations rely on assumptions, simplifications, and approximations. Without real-world experiments to validate them, they remain approximations rather than definitive answers. This gap illustrates why observation is irreplaceable in science. Having immense data sets does not automatically yield understanding. Data without theories is like a map without coordinates. Mountains of information can be collected, but without conceptual frameworks to interpret patterns, the meaning remains hidden. Scientists must combine measurement, analysis, and theory to turn raw numbers into knowledge, or the mysteries persist. Finally, physics itself imposes constraints on what can be measured or manipulated. Nothing can exceed the speed of light, and uncertainty principles in quantum mechanics set limits on precision. Energy, temperature, and scale all restrict experiments. These boundaries are not failures of engineering, they define the rules of reality. Recognizing them allows science to focus where progress is possible and pushes researchers to innovate tools, methods, and ideas that approach but never fully bypass nature's deepest mysteries.
Unanswered questions are the engine of scientific progress, driving researchers to explore, experiment, and innovate. Every mystery, from the depths of space to the workings of the human brain, pushes science to develop new tools, techniques, and ways of thinking. Far from being frustrating, these unknowns inspire creativity, encouraging scientists to approach problems from angles no one had considered before. Innovation rarely emerges from certainty. It thrives on gaps in knowledge, where bold hypotheses can lead to breakthroughs. History shows that future discoveries often arise from failure. Experiments that don't produce expected results still generate valuable insights, revealing limitations, anomalies, or patterns that guide the next attempt. Failed experiments are not wasted. They are stepping stones that refine ideas and deepen understanding. From vaccines to quantum computing, progress builds on iterations, mistakes, and unexpected outcomes, demonstrating that resilience and persistence are essential in the pursuit of knowledge. Curiosity outweighs certainty in the scientific mindset. Accepting that we do not know everything keeps inquiry alive, fostering an environment where questions are valued more than immediate answers. This mindset encourages exploration beyond conventional boundaries, driving research into areas that might otherwise remain unexplored. Finally, these mysteries teach scientific humility,
a recognition that no individual or technology can fully grasp the complexity of the universe. Humility fosters collaboration, open-mindedness, and ethical responsibility, ensuring that progress benefits humanity rather than simply serving ambition. By confronting the unknown, science not only advances knowledge, but shapes the way we think, inspiring generations to wonder, question, and explore. In embracing mystery, we unlock the potential for innovation, understanding, and meaningful progress for the future of humanity. Thank you for joining us on this incredible journey through the mysteries that science still cannot explain. If you enjoyed this exploration, make sure to subscribe to Relaxing Fact Studio so you never miss another fascinating discovery. Share this video on your social media to spark curiosity among friends. Give it a like to help it reach more viewers, and leave a comment to tell us what amazed you the most or which ideas sparked your imagination. Your support is what allows the channel to grow, continue producing high-quality content, and keep uncovering the universe's deepest secrets.